Welcome back, ladies and gentlemen. Today we're going to talk about something called continuous growth. And continuous growth comes about when there is a non-predictable specific time at which the interest or the growth is compounded. Like so far, we've been talking about money quite frequently, and that end value is something that is causes some complication. So if you look at our situations right now, like if here's a table of values where we've invested $1,000 at 8% for 7 years. And the only thing that I've changed is the number of times per year that interest is awarded. So in the first case where I'm doing it once per year, I'm awarding that interest at the end of that 1 year, and I get, a few extra dollars in the account actually quite a few extra dollars in the account after 7 years of doing so. If I award the interest more frequently, so monthly, 12 times a year, you'll notice that number goes up. I get more money because I'm compounding it more frequently, so I'm earning interest on the interest that I've already earned more frequently throughout the course of those 7 years, and I get a slight increase in my overall balance by the end. So you say, okay, well, if 1 was good and 12 is better, well, let's do it a lot. So then we say, okay, and this is the way it really does work in real life, is that we compound it daily at the end of each business day. So there's still a distinct time. I think it's like 3 p.m. or 4 p.m. where if you're going to be charged interest or you're going to be earning interest on a particular account, I think it's somewhere at the end of the business day. There's a specific time and day where that interest is awarded. And you look at the difference between monthly, which was 12, and daily, which we jacked that n up all the way up to 365 times. And all of a sudden, you notice that yes, we do get more money compounding daily, but it's not by very much. We only earned an extra $3 over the course of 7 years by performing this calculation 365 times instead of 12 times. So it looks like these numbers are kind of flattening out, and there must be some sort of limit to it. And just for the sake of experiment, if I were to compound interest every single minute of each of those 7 years, and you look at the difference between compounding daily and compounding every minute, you'll notice that these values are only off by a few pennies. Well, a dime and a few pennies, a dime and 1 penny, it looks like. So, so even though we've taken the extra step to do this calculation like hundreds of thousands of more times, it's not beneficial for the investor or the banker in this situation to keep it. There's got to be a better way. So there is. And it so happens that it involves this number E. And whenever you see a pattern in math where something is flattening out to a specific value, that probably means that there's some underlying value that the pattern is approaching. And in this case, it has to do with the number E. The number E is, it's about 2.71. I'd like you to remember that. It's about 2.7, roughly 3 if you need to throw it in a calculation real quick. But what it is it's what we call a transcendental number. It's a number that pops up in natural phenomena. It just happens, just like another number that you are aware of called pi. Pi comes about from dividing a circle's circumference by its diameter. In another way, this number E, which is a very precise number, comes about from doing compound growth on top of itself every instant of time. So if you were to compound it, not every month, not every year, not every moment, not every minute, but literally every instant, you kind of level out at this number. Now, to figure out what this number was, smarter people than I just ran a little experiment. Invest $1 for 100% interest for 1 year, but you're going to compound it continuously, eventually compound it continuously. And you see what this graph is a balance of the account after that 1 year. The x-axis is the number of times in that year where that interest was compounded. And, monthly is 12, daily is 365. So we're not even getting to the 365. And you can see already that the balance in the account is flattening out at exactly this number. So this is what we consider E to be. And it is basically a transcendental number that we observe even in nature that has to do with the growth of things that happens when there isn't a specific time at which that interest or growth is compounded on each other. So we end up with two formulas, so we can replace, what's really nice about this is we can replace all that complexity right there in our previous formula with just the number E. And that's where we insert that number E. And you say, well, I don't want to type out 2.71 and what 8, blah, 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 blah. And yeah, you're right, you don't. There's a dedicated button for it on your calculator. I'll show it to you, show you where to find that in just a moment. But you're going to have to make the decision, am I in a discretely compounded situation? Discretely means that it is happening at a distinct time interval that you can define, like every minute, every day, every month, every week, whatever it is. Or is it compounded continuously? Are there just so many things that they're basically uncountable, like the number of atoms happening in a reaction, the number of people in the population of Earth? Or is it just it may not even be that many things. Like you might have a population of like 100 rabbits, but as they repopulate, it's not like the rabbits all get born at midnight. Okay, they could pop off at any moment. They could become at any moment. So while we do have an average growth rate associated with that population, the moment at which that population grows in a compounded manner is kind of unpredictable. It's kind of random. So this formula that we're going to work with today is really good for anything where there is basically things are going off randomly. You have a huge population, or you have a huge number of things, or you have a non-distinct time interval, meaning you don't know the time interval where this is going to happen. It's going to happen random. Think of it like popcorn kernels in a microwave. You know there's going to be some going off. You just don't know exactly when they're going to go. Okay, it's not like they're going to go all at the 3 minutes and 30 seconds recommended time for microwaving popcorn. It doesn't work like that. That would be like saying, well, all the babies that are going to be born in the United States that should have happened in the first quarter, January, February, and March, are going to happen. They're all going to be born on March 31st, and that just doesn't happen. They just happen as they happen. You know, it's a natural phenomenon. It's a natural growth rate. So it is a naturalistic or a transcendental number. That is the point of what this number E is. So basically what E does is it replaces the idea that things are going to happen in a structured, ordered way, and it's going to introduce a little bit element of randomness to our situation. So you can see all the same letters are in play. So we have the amount in the account afterwards, or we're going to do population growth. Now we can expand this to more things. We still have a principal, we still have a rate, we still have a time. All those are still basically the same thing. The only thing that I will say is that time no longer has to be measured in years. Oftentimes it will be measured in years, but whatever time units you are given in the problem, you can just pop them right into the formula. You do not have to worry about converting 6 months to a half a year and so forth. You can just keep working with the time units that are given in the problem. So obviously, you're going to have to be able to type one of these things into your calculator. So we got to know where that number is. So E is stored in your calculator. It just knows it. There is a button for it on the cheapies. It's right there. On the graphing calculator, it is actually in two places. You have an E to the X button and you have an E button. By the way, on the cheapie, you only have an E to the X button. So if you want the number E just by itself, you would go E to the first power. And in fact, if you have your calculator available, I would make sure that you can find this button, type in either an E or an E to the first, hit enter, and make sure that you can get that 2.718 number. The nice thing about having this E to the blank function built into your calculator is that every time you use E, you tend to use it as the base of an exponent. So that's the way you need it anyways. But in the case that you do need E all by itself, there it is for you. This button right here, by contrast, will insert an E and a caret symbol. So still use parentheses if it doesn't pop up automatically. I forget whether it does or not. So let's do a first example. Wolves in Minnesota are making a comeback. This is a few years ago that I looked this up. The latest DNR survey in 2017 estimates the wolf population to be 2,655 and suggests an average growth rate of 8.5%. We're going to assume yearly. What will the population be in 2027 based on a continuous growth model? So we do the same thing that we did yesterday. We try to assign things. We would like to know what that is later on in the future. So I'm going to say that A is my question mark. my principal, my beginning initial amount. So we're not talking about money anymore, but we still kind of have an initial amount. We still have an initial population of 2655. The rate, they said 8.5%. And just like before, we have to convert that to a decimal. And then time, we want to go from 2017 to 2027, so that would be 10 years. And as long as that rate that they gave me was a yearly growth and our time is measured in years, I don't have to worry about the units on my time scale. So, and then it's just a matter of punching in. So we go, what we want is our principal, 2655 times E. So you're going to hit that E button, and depending on which button you press, it might give you just an E, or it might give you an E with the caret, but you do want to raise to a power, and you want to put parentheses around this. Our rate, 0.085 times 10. And if you take a moment, type that in, make sure that you can get this number with me. We should have a wolf population of 6212 in 2027, based on that continuous growth model, which is pretty outstanding. That's almost a tripling in population. Yeah, let's move on to another example. This one has a negative, so we're going to talk about depreciation. Depreciation is a good thing to model with this formula over the compound growth, the discretely compounded growth, because the longer you own something, the more it depreciates in value, usually. And there's no distinct time interval at which this is going to happen. It's just going to continuously decrease in value when you have this car being owned. Okay, so we can assign our variables. I barely have to read out the problem at this point. We're going to buy it for $23,000. So that sounds like an initial amount to me. It's probably going to be given to us pretty straight up here. We're going to go 19% per year. It's depreciating though, so we're going down. So I'm going to say negative 0.19. I'm going to convert it to a decimal just like we have, and then time is going to be 3 years. Punch that in. So amount equals principal 2,300. The nice thing about this formula today is that it is easier. I hope that you're finding it to be easier. Negative 0. Make sure you put that negative in there because numbers are going down. Just think about that in the context of each problem as you go along today. And if you punch that into your calculator, make sure that you can get this number. It is a 13,007.09 right there. So after 3 years, your $23,000 car has lost basically $10,000 of value based on that. Although I will say Honda's probably beat that depreciation rate by a little bit. And lastly, we've got one about time. This has to do with carbon dating. How do you figure out how old something is when they do that? They know that the decay rate of a particular molecule, or actually an atom, in all living things should have this amount of carbon-14 due to the carbon cycle. If you learned about that in biology this year, there's a carbon cycle. We assume that there's going to be this amount of carbon in all living things. And after they die and get buried, they no longer have exposure to the carbon cycle. And so that the amount of carbon-14 in them decays very, very slowly. So this is like every year, they only lose that little bit of a percent, but that's how it works. So let's say an archaeologist scrapes off a pigment sample that recently discovered in a cave drawing. The sample that they grabbed off the wall has about 16.291% of what you would expect in a living thing. That means that thing's been not exposed to the carbon cycle for a long time, or we'll say dead for a long time. In this case, we want to figure out where it is dead. So this one's a little bit tricky because we start with this. This is the ending amount, right? The 16.29%. And this is not a rate this time. This is the portion of carbon-14 that we found at the end. So oddly, we're just going to use this percent as a quantity, more or less, saying, hey, there's only 16% of the carbon that should be there. There should be 100. We started with 100. So in fact, we're starting with 100%. That becomes our principal. That wasn't even in the word problem, so that was a little tricky. And then we have this rate. Okay, so this is going to be ugly because we got to move that decimal place over. So we got to go point. I'm going to go 0, 0. So basically, I'm just moving this decimal place over 2 spots, just like that. So I'm going to have 1, 2, 3 zeros before the numbers even start. 0, 9, 6, 8. Whew, gross, but doable. And then time is the question mark in this case. Okay. So I do my best. This is one where we're going to have to do by trial and error. I know that the ending amount should be 16.291. I started with 100, multiplied by e raised to the negative 0.0001200968, and then times t, which I don't know. So basically what you're going to have to do when you solve a problem like this, there is a cleaner way to do it, but to get us started, this is you're going to have to plug in a value for t and just take a guess. Now, this is an old thing, and you'll probably quickly learn that it's older or younger than you think it is, but basically you just guess and check. And if you plug in a t value of whatever it is, let's just say try 10,000 years old, and you have a number bigger than this, that means that you want to choose an older year because you want to decay that more. So if you plug in t equals 10,000 years old, you're going to get something like, I don't know what it is, but you'll get like 20% remaining, which is too much. So you need to go older. So then you try t equals, 20,000. And then you'll get something, the real answer. I know the real answer because I've worked this out in previous, but you'll get something like 13%, and that's too little. So then you got to go halfway in between. Just so happens that a t value of 15,000 just by trial and error will get you basically dead on to that 16.291% value. That's what I've got for you today. You have a worksheet to do, and I'm signing off. Have a great day.